My guest today is Patrick Frank.
Thanks, Tom. I'm honored to be here, actually. I wanted to let you know that too. Let's see. I have a PhD in chemistry from Stanford University, bachelor's and master's from San Francisco State. And I've spent most of my career doing at the SLAC National Accelerator Lab and also the Department of Chemistry at Stanford, doing inorganic biochemistry, which is the biochemistry of trace metals, and mostly using X-ray absorption spectroscopy, which is a big X-ray source at SLAC. It's tunable, and you can tune it to different elements and look at them specifically in biological samples or wherever you like. So I've done a lot of that. I'm pretty much retired now. So that has let me go off in other directions, which are non-chemistry and pretty unusual. And one of them is climate. And I should just say that I began looking into the climate business in 2001, a long time ago, because the third assessment report had come out and there was a lot of polemics about it, accusatory polemics. And I wanted to find out for myself whether there was really anything to worry about. And so I started reading the literature. And you can interrupt me whenever you like if I'm taking too long here.
No, this is all good.
Good. All right. So I started reading the literature, and after a couple of years, I ran across this paper by Willie Soon and Sally Baliunas and Craig Idso and others about the uncertainties in climate modeling. And I'd been, struggling until then, and that suddenly caused the scales to fall from my eyes. I knew how to think about it. And I noticed that all the climate modeling papers didn't have any physical error bars on them. It's like they weren't doing anything about the reliability of their own work. So I started investigating that. And by 2008, I had published a paper in Skeptic magazine, actually, about climate model reliability. And a couple of years after that, I published on the global air temperature record because I realized that they were assuming that all the measurement error was random and averaged away to zero in the temperature readings, which is, as an experimental scientist, I know that it's nonsense to think that measurement error is all random and goes away. It's impossible. So I've done a lot of work on climate modeling reliability and the reliability of the global air temperature record, which actually brought me to your attention. And that's why I'm here now today. I'm going to be talking about both the climate model stuff and the air temperature stuff. And there are only about 6 or 7 slides, so it should go pretty fast. Okay, so here we are, the Tom Nilsson podcast on the reliability of carbon dioxide climatology. So I'll go into the climate modeling business first. So question is, part 1, are air temperature projections reliable? So let's see, can you see my little arrow there?
I can, yes. Yep.
Good. So this little linear equation here will successfully emulate the air temperature projections of advanced climate models running on supercomputers. So if you wanted to run an air temperature projection yourself, you could do it on your hand calculator. So in words, this equation is the temperature change, delta T, is equal to a sensitivity function, FCO2, times the basic greenhouse temperature, 33 degrees Celsius, times the fractional change in forcing, this one. So this is the basic forcing, and there's the fractional change in forcing, or the change in forcing, and you divide it by the basic, and you end up with the fraction. So you plug all that into this equation, and over here, we have the emulation of a whole bunch of climate model air temperature projections, 10 of them actually. And these are showing what supposedly will happen if carbon dioxide increased at 1% per year. And this little pink line running right through the middle that doesn't have any noise on it is the emulation. And you can see that this equation has put a line right through the middle of the climate model air temperature projections. So the one on the right are slightly more advanced climate models, and they are looking at the special report on emission scenarios model, A2. And again, you have 10 different climate models, and you see that they all make different projections using the same forcings, but that's them. And right through the middle of that, this line without any noise in it is the emulation produced by that little equation with FCO2 equals 0.42. And that 0.42 actually comes, it's not just an arbitrary thing that fits to those lines, it's actually derived from the work that Manabe and Weatherald published in 1967. So the paper that I published all this stuff in the supporting information, I show that derivation. Okay, so
I think this is mind blowing. That's it. That's how they're modeling the climate in the year 2090. It's just
it's a linear extrapolation of greenhouse gas forcing. That's it, all of it. So these models are enormously complicated with lots of partial differential equations and and turbulent flow and all this stuff. And what comes out, what goes in is forcing, and what comes out is just a linear projection. So it's all linear, all of them. So the next one, so here we go to advanced climate models. Those previous ones were the CMIP3 generation. So the one on the left here, we're using the same little equation. And here we have the projections of CMIP5, coupled model intercomparison project generation number 5 climate models, which are the ones that went into the fourth assessment report of the IPCC. And you see that we have four different scenarios there, and they all line up for the change in temperature during the historical period. And then here we have the projections for all these 3 or 4 different scenarios. And the points are generated by the climate models. In this case, it's the, which one is it? It's the GISS, Goddard Institute for Space Studies model E2RP1. Did all of these, and those are the points, and the lines going through there are produced by this little linear equation. So the one on the right now is the CMIP6 generation. It's the current generation of advanced climate models, the Alfred Wegener Institute model. And the points again are produced by the model. And here we have the SSP simulations, which are the, what are they called? The social something or other, special social, so there it is, shared socioeconomic projections. So those are the advanced scenarios over the previous representative concentration pathways. So they're of course much better. So again, you see that the lines produced by that little linear equation goes right through the middle of all of the points of the advanced climate models. So they're all just right up to the present, just linearly extrapolating forcing in order to produce their projections. So now we talk about when the scales fell from my eyes and I started thinking about projection error. So over here on the left, we have this little bar chart. And right here, this little line is actually a bar, and it shows the change in forcing every year from greenhouse gas emissions. It's 35 milliwatts per square meter per year, the increase in forcing. So the larger one here, the first blue one, the dark blue one, is the uncertainty in the thermal content of the atmosphere produced by CMIP5 models when they simulate the troposphere. So it's mostly because they do a poor job simulating clouds, and clouds really control the thermal content of the atmosphere. So if you get the clouds wrong, you get the thermal content wrong. And so this thermal content, this uncertainty in thermal content produced in the atmosphere during the simulation of the climate by CMIP5s completely dwarfs the increase in forcing due to CO2 emissions. And so if the uncertainty is much larger than the forcing, you can't tell what the forcing is doing to the climate. And so this difference is 114 times, plus or minus 114 times longer than the change in forcing per year. So that's the CMIP5 version. The CMIP6 versions over here on the right, it's like lighter blue, is a little bit better. And that's only 83 times larger than the change in forcing from greenhouse gas emissions. And so, so how do we turn these uncertainties here in thermal content of the troposphere into some kind of an error metric when you do a projection, an air temperature projection? So we, going down to this little equation again, we know that this equation produces really good emulations of air temperature, of climate model air temperature projections. And so if we want to put the uncertainty due to thermal forcing into that equation, you do it right here. There's that uncertainty, and it goes right into, it's the uncertainty and forcing in the troposphere. So we put it into the part of the equation that includes the forcing. There it is, plus or minus u. And when we propagate that error, and it propagates step by step by step, each step in an iterative propagation, you end up propagating the error in each step as well. And the error accumulates, the uncertainty accumulates from step to step to step, because each step in an iterative calculation carries forward the uncertainty of the previous step. So we have that result over here on the right. Here we have the CMIP5 GISS model again, and you see the little inset is the projection by the GISS model, and the blue line is the emulation. Does a really good job of emulating it. And when you have plus or minus 4 watts of uncertainty in the troposphere with every single step of a projection, when you propagate that error out, you get this very large uncertainty envelope, because the uncertainty in the temperature, air temperature, is 114 times larger than the change in forcing. So you have this enormous uncertainty bar. And you see at the year 2100, the bars are plus or minus 17 Celsius. So that doesn't mean, I have to really say this, that does not mean that the projection is saying that temperature in 2150 or so could be 17 degrees warmer or colder than it is today. That's not what an uncertainty bar means. It means the uncertainty is so large that we have no idea what the temperature will be in the year 2150. No idea at all. And the projection from the model isn't telling us anything about what the air temperature could be at some future date. That whatever the temperature will be, it's lost in the uncertainty. So this is CMIP5 models, and you can see that the air temperature projections from this model have no physical meaning at all, because whatever the change in temperature is going to be is completely lost inside the uncertainty produced by the simulation error that the model is making. So the one on the bottom is a CMIP6. Again, it's the Alfred Wegener model, the most advanced of the climate model generations. And the inset down at the bottom again is the air temperature projection points. And the blue line is the simulation produced by that little linear equation. You see, all you need is the forcings, and it just goes smack right through the points from the model. And so once again, we put this time the CMIP6 annual long wave cloud forcing error, which turns out to be plus or minus 2.9 watts per square meter, 83 times larger than the forcing change. And you propagate that uncertainty through the air temperature projection, and you end up with an uncertainty of plus or minus 16 degrees in year 2100. And that means that the air temperature, whatever it is lost inside that uncertainty bound, and we have no idea what carbon dioxide or other greenhouse gas forcings will do to air temperature over 100 years. It's a completely invisible result.
Well, Patrick, I do have a question about that little inset for your CMIP 6. So they don't correctly get that 1940s to 1970s cooling that happened in the real world? I don't really see that in the in that little inset.
What 14 to 1970s? Oh, I see. It's actually there, but the scale is so small that you can't see it.
Okay.
And I should say that the propagation starts in year 2005, the propagation of air, but actually the entire length of the air temperature line is a projection line. It's not a historical climate line. But what they do is they tune the model in order to reproduce the climate, and then they publish the modeled climate rather than a modeled historical climate rather than the actual historical climate. And so when I emulate that, I'm emulating the model reproduction of the historical climate. And actually, I've taken the IPCC forcings for the 20th century, plugged them into that little linear equation. It does a pretty good job of reproducing the entire air temperature change since 1900. Anyway, so that's a shocker, right? A linear equation will reproduce everything that climate models will do with air temperature projection, and you can use them to propagate the error in the tropospheric, the simulated tropospheric thermal content, and show that the uncertainty is so huge that the air temperature projections have no physical meaning.
So maybe I missed this, but did you hard-code it into the models? Is there a climate sensitivity to doubled CO2, a certain number of degrees we should get of warming?
No, the climate models do not have a sensitivity. The sensitivity emerges from however the climate model is constructed. But there's a real problem with climate models about that, because all of them are able to reproduce the 20th century air temperature trend. They're tuned to do that, actually. And as soon as you remove the constraint of the historical temperature, they all go zooming off in all kinds of directions. And you go back here and you can actually see that. These anomalies, these projections here are all working on exactly identical forcings. And you can see that there's a spray of model projections that crosses about 3 degrees after 100 years or so. So they all have different climate sensitivities, even though that they supposedly have the same physics and they have the same forcings. They still produce a spray of projections. And there's another thing that's weird here too that doesn't pop out immediately, but these are anomalies. They're not actual temperatures. They're the changes in temperature. And so one of the big assumptions in climate modeling is that the error in the modeling is the base state error in 1850 when they spin these models up, and then you project them out across the 20th century. If you subtract the projections from the base state, you're supposed to get a really accurate temperature change projection, right? But that's what these have already had. They've had their base state error subtracted away, and they still go zooming off all over the place, right? So the error doesn't subtract away. We don't know what the errors are because nobody knows what the errors are, but we do know that the models don't reproduce one another.
How would a person go out actually trying to model the climate? Can it be done?
You know what the problem is I've actually seen this in a paper written by Gavin Schmidt. He has an all or nothing view. You either leap to a theory of the climate from like zero, or you don't have anything. You have to have either the complete physical theory or nothing, right? So the whole idea of the reductivist program of science, where you start by studying the things that you can study, the small things, and you work your way up until you finally get a general theory. That's how it's always been. But in climate modeling, they don't want to do that. They want to just leap out to the theory. And so to specifically answer your question, the physical theory is completely lacking for for the climate. They don't know how the climate works. And the physics is extremely difficult. The microphysics of clouds can't be described. And the whole hydrology cycle, where water evaporates from the oceans, is convected up into the upper atmosphere, condenses into clouds. All of that process is undescribable. Can't be described in physics yet. So, it's even worse than that. Most of the energy is held in the oceans. So the ocean circulation has a huge amount to do with the way that energy is transducted around the globe, and it really controls the climate energy state. The ocean does. Well, the ocean is modeled as the thermohaline current, and I'm sure you've seen pictures of that with these currents sweeping from the equator up to the north and down to the south and all around and everywhere. So, and that's what goes into the models. So some years ago, somebody decided to see whether or not they could measure that current. And it was really hard, apparently. They had a hard time getting the project funded, but they eventually did an abbreviated project, but they were able to drop something like 1,000 neutral density buoys off of Brazil into the water, and they would go down, between 2,000 and 3,000 feet or so, and drift with whatever the current was, and then come up every day and report their position. And so they published the result, and what they wanted to see was the slow drift of the thermohaline current, bringing all of these neutral density buoys to the poles, where the heat would be dropped off. But that's not what happened. What happened is, if you look at the trajectories, they spin up and then they go down and then they go around and around and then they go over there and then they go over there, and there's no drift. There's no detected thermohaline current at all. So however the ocean is mixing itself is incorrectly modeled in the climate models. Carl Wunsch, who's a very well-known marine physicist, probably the most prominent one in the world, said that oceans do most of their mixing at the periphery, where the waves do all this stirring, and but that's not included in most of the climate models, all of that mixing. So how the energy is transducted around by the oceans is not well known at all. So the climate energy state can't be solved. So it's nobody's studying it the way it should be studied. It's really frustrating to me as a physical scientist, and I'm sure is to you too, that there's no real research effort going on to study the climate in details. Instead, we just have larger and larger supercomputers that they put the same deficient models in and get their wrong answers faster. So that was a long way of answering your question that no, climate physics is deficient. The models can't reproduce the climate, and it's all just speculative. But the big problem is that you've got computers now that can produce really wonderful false color images of the globe with blue oceans and white clouds and brown and green surfaces and so on and so forth. It looks really real, but it's not. So that's what the problem is. You have convincing nonsense is what you've got.
I think you mentioned elsewhere that Dick Lindzen has also mentioned that Earth's temperature can vary without any external forcing at all. If humans didn't exist and nothing changed on the sun, still the temperature might fluctuate, correct?
Yeah, that's correct. And that's in fact the case. And it's happened in history, right? The medieval climate optimum, the Roman warm period, the Little Ice Age, and so on are all perturbations in the climate that happened when the sun didn't do anything at all, except a little bit of sunspot variety, but certainly no carbon dioxide. But yes, the temperature can vary without any change in forcing. And if you think about it, the climate subsystems are a bunch of oscillators, right? You've got the El Nino oscillation, you've got the Madden-Julian oscillation, you've got the North Atlantic oscillation, the Pacific decadal oscillation, the Indian Ocean goes through an overturning cycle. There are oscillations all over the place, and they're all beating against each other, and they're all energetic. So when you have a bunch of coupled oscillators, including the atmosphere, they can swap energy around without any change in the total energy state. So you can have temperatures going up and down and all around without any change at all, because energies are flowing in and out of these oscillators, relative to the other ones. And it makes a lot of sense. But you never hear anybody talk about that. And so you can have big changes in the climate without any change in external forcing.
Do you think anyone on Earth actually understands what has caused the Earth's temperature fluctuations, even over the last 6,000 years? Why actually it warmed and then cooled around the medieval climate optimum, all that type of thing?
No, nobody understands it. I mean, you'd have to have a really good physical theory of the climate that's able to map out the change in the energy state down to some pretty small number, especially for the atmosphere, because small changes have, large consequences. When the total heat is, the total thermal content is small, then small changes can make large effects. The clouds change a little bit. A 1% change in cloud would have a very large effect on the thermal properties of the troposphere. But even the visualization of clouds from satellites is only good to plus or minus 10 or 15%. So we can't tell what the clouds are doing. So did that answer your question?
It did. It did. So I guess we're going to be surprised, or humans are going to be surprised between now and 2100. Nobody really can predict what's going to happen. We're going to have to wait and see.
Yeah. The Younger Dryas event, which was this huge cooling event that happened about 8,000 years ago. Things returned to the glacial conditions. You had a drop in temperature of several degrees, and it lasted for about 1,000 years. And there are big fights about how that happened. Some people say a bolide came down and caused the climate to go through loop-de-loops. And other people say, no, it was, some volcanic thing, but nobody knows. And it was a gigantic perturbation on the climate, a big one we ought to be able to talk about, or at least resolve out of our theories, but it can't be done. So if a 10-degree change in climate that lasts 1,000 years can't be calculated from some physical theory, how are we going to change calculate 1 degree across 100 years? And not only that, but there are these Heinrich events. Are you familiar with those Dansgaard-Oeschger events?
I can't tell you what they are now.
Yeah, those are, nobody knows why those happen either. And the last interglacial had a lot more of them than this one does. But there are sudden increases in temperature where the temperature change can be 10 times what we're experiencing now. 10 degrees in a century. Temperature goes up in the climate, and then it decays down across about 1,000 years. And then, some few thousand years later, it happens again. And they're recorded in the ice cores, these Dansgaard-Oeschger events. And they're huge rates of warming and then slow rates of cooling over and over and over again. Nobody knows why those happen. And they dwarf what's going on now. So, the natural variability of the climate is much larger than we've seen in the historical time of the Holocene. We live in a very stable climate right now compared to just about everything that's happened for the last 2.5 million years.
So there does appear to be this bedrock assumption that absolutely for sure in the year 2100, it's going to be warmer than it is today. The only question is how much warmer it's going to be. But do you think that there is a real chance it's going to be colder? I do. In the year 2100, maybe it'll be colder than today?
It could be. Nobody knows. The climate models can't predict it. And in climate, when you don't have a theory that predicts what could happen from changes, things that are going on, perturbations, what have you, you start looking at history to see how things have changed in the past. And when you do that, you find out that whatever's going on now is completely within natural variability. And so given that, the fact that we don't know anything, it might be warmer in 2100, it might be cooler, nobody knows. It turns out that if you take the air temperature record, you can do a really good job fitting the historical change with two oscillations, one of them about 70 years and one of them about 250 years. A very slow oscillation. That's the rising part, and then you've got some wiggles on top of it. It's really easy. And so if that's correct, that you've got a long period oscillation and a short period oscillation that are controlling the temperatures, and you plot that out, which I've done, the temperature is going to go down by the year 2100 because we're on the top of the long period oscillation right now. And it's, if it goes back down again, then things are going to get cooler. And there are going to be, 70-year oscillations on top of the cooling period. But that's all totally empirical and has no physical basis at all. It's just a curve fitting on the temperature record.
So if you do that curve fitting, though, how much cooling would we get if that actually does happen again? Is it enough so we can't grow wheat in Canada as easily?
Yeah, it would be. The thing predicts about, well, it doesn't predict, but it says about 1 degree colder than now, which is, which close to Little Ice Age again.
Wow.
Yeah. So it would be difficult to grow wheat in Canada. Yeah, and the Thames would freeze over.
Okay. Before we move on to the rest of your presentation, I have one more question. You mentioned that you had an article in Skeptic magazine in 2008. This is Michael Shermer's magazine, right?
Yeah. Yes, it is.
So that was a better times, right? You couldn't put that in there now, could you?
No chance. I tried to put something in about air temperature when I worked on that. He wouldn't have it. And I don't know how much of this I should go into.
Up to you, whatever you want to do.
Well, I've also been doing some work. This is going to sound strange because I'm a chemist, right? I'm a physical scientist like you. But I've published a paper on sexual harassment. And I have another, and it was, it's a good paper, and it looks at sexual harassment in the academy in the context of the 2018 National Academy of Sciences report on the sexual harassment of women in STEM fields, which I read that report. It's probably the most incompetent piece of reportage I've ever had the unfortunate experience of reading. So that actually caused me to study it, and I ended up publishing a paper on it. And I sent I sent an article, a manuscript, to Michael Shermer, and he liked it, and he and his editor edited it some, for more objective language than I had in it, and it was going to be published this month in August. And then he came back and said, well, he says, my editors don't like it because they are afraid that if we publish that paper, people are going to think that we are not worried about sexual harassment. Well, so he dumped it. He then, after he accepted it, he turned around and declined it. And so it's pretty upsetting, really. So he doesn't take anything about critical climate change anymore. I know because I've tried to publish stuff with him. And he doesn't take anything that's really controversial in the sense that, if we were living in 15th century Europe and you wrote an article that said witchcraft isn't true, that's where he is with respect to climate change and sexual harassment. He just can't bring himself to publish anything that contravenes standard practice.
Interesting stuff. Okay.
Yeah, really. Yeah.
I may have derailed you long enough. Should we go on to part 2 here?
Yeah, you're welcome to edit that out.
No, I'm going to leave it in. Okay.
All right. So let's proceed here. So part 2, the global average surface air temperature record. And I just published a paper on this. So here we have pictures of the standard sensor boxes that are deployed across the world today. Originally, was the Cotton Region shelter, this square wooden box on the left and in the middle, that was developed around 1870 or so. Before that, there were a whole bunch of different ways that people put thermometers out in order to measure air temperatures, and it was eventually standardized to this. It's a louvered box. The thermometers are inside, as you can see in the middle. It's a very basic minimum and maximum air temperature thermometer that's in there, and they're consulted twice a day. Well, once a day, really. The thermometers are built so that when the maximum goes to its maximum temperature of the day, the mercury column will stay there. It doesn't come back down again. It's like remember the old fever thermometers, the mercury fever thermometer? Yeah. So they had a little pinch at the bottom in the capillary, so that when you took the thermometer out of somebody's mouth, whose temperature you're testing, the mercury column doesn't go back down again because the restriction in the capillary prevents it from doing so. So there's a restriction like that in the mercury thermometer of Cotton Region shelter, also called the Stephenson screen. Stephenson is the guy who actually invented it. And the other thermometer, they use the mercury thermometer to measure the maximum of temperature. And the minimum of temperature, they use alcohol thermometers because oftentimes in many places, the air temperature will go down below the freezing point of mercury. So the thermometer becomes useless. Mercury is at about minus 38 Celsius. It freezes. So they use alcohol instead. And the alcohol capillary has got a little tiny rider that sits on top. It's a metal rider that sits on top of the meniscus of the alcohol. So when the alcohol goes down, because the temperature drops, the rider goes down with the meniscus. And then when the temperature goes back up again, the alcohol finds its way around the rider and goes up around it, but you still have this rider sitting down there at whatever the minimum temperature was. So every day somebody would come out and they would look at these thermometers and they'd get the maximum temperature and the minimum temperature, and then they would have a spinner and they would spin the thermometers around to force the mercury back down to where it should be and force the spinner back to the top of the alcohol meniscus again. So every day that you had to have that. And after about 1980, those thermometer boxes, the thermometers in the boxes were phased out in favor of the MMTS sensor on the right, which is a thermistor. And thermistors are actually accurate to about 1/100th of a degree or so. The thermometers, the mercury and the alcohol thermometers, were typically 1 degree per division. So you had to really squint down to get fractions of a degree. The difference, the height between the scores on a 1 degree per division thermometer is about 1 millimeter. So you really have to squint to see fractions of a degree. The thermistor is an electronic sensor. So you can actually sit in your living room and you've got an electronic readout that's connected with a wire to your thermistor there, and you can read your temperature in the comfort of your office instead of having to go out in the snow or the rain and read the daily temperature. But the downside of that is nobody wanted a really long wire to go out to the thermistor, and so they actually put those closer to buildings and so on in order to minimize the distance that the signal had to travel. So and the major thing about these, apart from, which we'll get to, is the accuracy of the sensor itself. But both of these, you notice, are just louvered boxes. The MMTS has louvers in it. The box has louvers in it. And so in order to measure the air temperature, the air has to be moving through those louvers and bathe the sensor in the external air in order to get an accurate temperature of whatever the external air temperature is. And that requires wind. So there has to be 5 to 10 miles an hour of wind at the side of, impacting the side of any of these in order to move enough air through the box in order to bathe the sensor, the thermometer or the thermistor, in the same air as is external to the box. You have to have wind moving through it. It's typically, they usually measure these winds at 10 meters, and it has to be 10 meters per second at a 10-meter height in order to properly bathe the thermometer or the sensor in external air. And a 22-mile-an-hour wind, that's pretty breezy. So if it's less than that, what happens is the sun is shining all the time on these boxes, on these louvered shields. And on a warm, sunny day, they warm up quite a bit. And the temperature reading will be wrong because it'll heat up. The box gets heated up, the air inside the box gets heated up, and the temperature is wrong. So you get the wrong maximum temperature. And that even happens when there's snow on the ground. If you have a winter day where the sun is shining, even though it's cold outside, the sun is shining and gets reflected off the snow albedo, and it reflects up to the bottom of the box and warms it up. And you can get a temperature that's a degree higher than the cold temperature of the day because of reflected sun coming off of snow. So these are all things that people in the 19th century knew about and they worried about it. But since about 1950 or so, nobody worries about that anymore. You never see any discussion of that in the literature about air temperature and its global average.
So how much warmer could it be, worst case, on a very still hot day? Where if it's how much warmer could it be in the box versus what?
People have recorded increases of about 3 degrees warmer than the air temperature.
Would that be Celsius or?
Celsius, yes.
Wow.
Okay. So that's about 5 degrees Fahrenheit. And on a cold winter night, if you have a clear sky, then the boxes can actually radiate off into the clear sky and get colder than the air temperature. And that's actually happened too, although it's rare, more rare. So So here we're going to talk about the accuracy of temperature measurements. So the box on the left side is the intrinsic accuracy of a thermometer. So you have a thermometer, mercury thermometer, you're in the lab, it's 1 degree per division. How accurate is it? So there are several things that can happen. You have the intrinsic accuracy of the thermometer itself. You've got a little capillary in there. How uniform is that capillary? Is there a little bit of grit inside there, or is there not? Is the mercury really clean, properly clean, or is it not? There are things that happen, and it turns out that people have spent a lot of time calibrating thermometers. And when you're in the laboratory, if you have a 1 degree per division thermometer, the best you can get is about plus or minus 1/10 of a degree. And beyond that, the thermometer that's the detection limit of a thermometer. Any movements of the mercury column smaller than that have no physical meaning. So that's an empirical limit. And the National Institute of Standards and Technology has taken that limit, has measured that limit, and other people have too. So that's the bar for thermometer accuracy over on the left. The red bar over there is the accuracy limit, the intrinsic detection limit of a 1 degree per division mercury thermometer. And these are 2 sigma, so that's double the plus or minus. So it means the 95% accuracy instead of the 68% accuracy. So it's about it's almost 3 degrees, so which means plus or minus 0.15. So then you have visual repeatability. So there you are, you have your thermometer in the lab, and you want to read what the temperature is, and it's a 1 degree per division, and the splashes between the degrees is only a millimeter. How closely can you see that if it's in between? And that number is typically about 1/4 of a degree or so. And finally, there's the problem of nonlinearity. It turns out that the expansion of alcohol or the expansion of mercury when it gets warmer or colder is not linear with temperature. And the mercury, the nonlinearity is actually pretty small. Mercury is quite good, but alcohol is not very good. And across 20 degrees, the nonlinearity can be as much as half a degree. And so the nonlinearity of mercury and alcohol thermometers is not corrected in the historical record. And so since all of the minimum temperatures are measured using alcohol thermometers and all the maximum temperatures are measured using mercury thermometers, those nonlinearities enter into every daily temperature mean, right? The maximum plus the minimum over 2. And if you have some uncertainty of half a degree in the minimum temperature because of the nonlinearity of alcohol expansion, that goes right into that uncertainty goes right into the mean. So the purple bar is the total thermometer uncertainty if it's measuring temperature, which is essentially a kind of sum of all of these 3 different uncertainties that go into that affect thermometer accuracy. And you put them together, it's the purple bar, and that includes half the nonlinearity of alcohol thermometers, which enters into a temperature mean, and half the nonlinearity of a mercury thermometer, but includes full visual repeatability and the full thermometer accuracy. And that uncertainty down at the bottom here is plus or minus about 4/10 of a degree. So if you're in the laboratory and you have a 1 degree per division thermometer and you want to measure a temperature, you're not going to get it better than a 1 sigma of about plus or minus 2/10 of a degree. That's it. So that number is actually the detection limit of the laboratory detection limit of the thermometers is actually larger than the quoted uncertainty in the global air temperature record. So they're quoting uncertainties that are smaller than the detection limit of the thermometers they're using. But we'll get to that in a minute. So that the other problem, the big problem is that when you're measuring air temperature out in the world there, you're not inside a laboratory. You're out in the field, right? Where the sun is shining on your box and the rain is falling and maybe there's wind and maybe there's not, and maybe there's clear sky at night and maybe it's cloudy and maybe there's sun reflecting off of the albedo and maybe there are trees that are nearby that are blocking the sun. or maybe there are buildings nearby with, that are blocking airflow, what have you. But people have done calibration experiments where you put a Stevenson screen with a thermometer out in the field, and you have a standard thermometer out there as well in an aspirated shelter, which means that you have a fan out there that's pulling air through the shelter so that you really do get a good bathing of the thermometer in external air. And if you have a very good thermometer in there, or a sensor like a platinum resistance thermometer, then you actually get a pretty good air temperature, good to plus or minus about 1/10 of a degree, or maybe even 5/100 of a degree. And you can use those to calibrate the thermometers in Stevenson screens or in MMTS thermistors, which are not aspirated, they're naturally ventilated. You can tell how well they do during any given day. And if you have a calibration that goes for a month or a year, you get a good idea about the accuracy of the deployed thermometers, through all 4 seasons. People have done that. And so here they are, right? So when you have a mercury and an alcohol thermometer inside a cotton region shelter, a Stevenson screen, the box there on the left, it has to face the sun, it has to face the wind, it has to face all these external environmental variables that go up and down and all around. And so the air that's produced in the thermometer reading is about plus or minus 0.5 degree Celsius because of the external environmental variables. And on the MMTS shelter, the number 2 there, the blue one, it's about the same. It's a little bit better, but it's about the same, about plus or minus 0.5 degree. And then you have, land surface is only 30% of the world. And if you want the global air temperature, you have to include the air temperature over the oceans too. And typically the assumption is that the temperatures of the air over the oceans is about the same as the temperature of the surface of the ocean. But there's thermal exchange there across that barrier. And so if you measure the sea surface temperature, you get a good idea of the air surface temperature above the ocean. It's actually much more complicated than that. Because I'll just say quickly that the part of the sea that exchanges energy with the atmosphere is about the top micron, right? Where the molecules of water, the ones that have a lot of energy, get to the top and radiate away their energy. But they have to diffuse up to there. So the diffusion, you have a very slow diffusion rate, and so it turns out that the equilibrium interface between the oceans and the air, the atmosphere, is about a micron or 2, maybe 10. And then you have, I won't go into the thermal structure of the ocean or anything like that. We'll just leave that there. But what people do in order to measure the sea surface temperature, there are a variety of different ways that people do. The major 2 is first by buckets, where people on ships would throw a bucket overboard, haul up some water, stick a thermometer in there, and measure the temperature and call that the sea surface temperature. If you don't do that carefully, and don't protect the bucket from the wind, for example, then wind will evaporate the water away and the water will get cooler within minutes. And so you measure a colder temperature than is really there. And if you measure it in the hot sun, if you're down in the tropics, the water might be warmer. So people have calibrated buckets, and if you do the job really well and protect it from the wind and the sun and do a quick haul and so on, then buckets are good to about plus or minus 0.15 of a degree, if you're really careful, bucket temperatures. And so that bucket temperatures dominate the sea surface temperatures all the way up through about 1930 or so. And then after that, people started getting lazy, and they were using the cooling water intake thermometer, getting their sea surface temperatures from the ship engine cooling water intake. There's all these ships have a big engines in them to drive them through the water, and they have to cool them off with seawater. So they suck seawater in, pump it through the engine, and run it back out again. And they always have a thermometer sticking in the water intake pipe in order to measure the sea surface, the ocean temperature, water temperature that's going through their engines. So those thermometers, mostly they're not very good thermometers, but nevertheless, you still get numbers. So people have taken those numbers And they use those instead of, the buckets, include them with the buckets. And you've got millions and millions of engine intake temperatures because you've got thousands and thousands of ships every day taking multiple temperatures. And over a period of a year, you've got millions of them. And the theory is that you add all those temperatures up, millions of them, all the error averages away to zero. Because sometimes they're reading too high, sometimes they're reading too low, and it all averages away. So there's this hand-waving argument about that.
So I did think I've read in the past about people admitting that they were in charge of actually getting the buckets to get the sea surface temperature. And when the weather was bad, they would just make up numbers. Have you heard?
That's happened.
Yeah. Okay.
And some of the engine intake thermometers, a few of them are, 1 degree per division, but most of them are like 2 degrees per division, and some of them are 5. And so nobody pays attention to what the thermometers were like on the ships in the historical record. Nobody knows. And so it's just all assumed that the errors, okay, it's a 5-degree thermometer. Somebody records a temperature. Sometimes, typically, the thermometers are very near the floor so that the engineer would have to get down on his hands and knees to read the temperature. And maybe they didn't want to do that. And maybe their parallax wasn't really great. They don't care aboard ship. They just want to, like within a degree or two, and they're happy with that. But if you're a climatologist, you want your degrees to within plus or minus 1/10 of a degree. And so in order to achieve that, they assume all the error just averages away. So the third way of people measuring temperature in the seawater, the sea surface, is bathythermographs. That's a minority of temperature, but I just included it for completion. That's usually good to about plus or minus 0.15 of a degree. They're pretty good. There's ones called expendable bathythermographs that have more problems, and I didn't include them in any calculation. So we have here now on the left. Now we have the intrinsic accuracy of thermometers under laboratory conditions, and on the right we have the kinds of uncertainty that happens when you start measuring temperatures out in the field and have to deal with wind and rain and sun and all these other horrible things like tossing around on a ship and inside an engine room and so on. So in order to get an uncertainty at a global air temperature, all of these have to be combined in proper proportion, which I've done. And so here comes that. So first one on the left is the way that air temperature is published. This is what we always see. The change in air temperature, there are anomalies, which means that they're the change, not the actual temperature, the change in temperature. And the red error bars are the published uncertainties that follow from the assumption that all the measurement error is random. And so those errors reflect things like imperfect coverage of the surface of the globe, and site movements where they move the thermometer on some surface station gets moved for over a few miles, and it measures a different climate and so on. So those are physical errors that involve measurements that do not include the measurement error of the device itself, of the instrument itself. There's no instrumental error in the published uncertainties. And so you can see that they go from 2 degrees plus or minus 0.2 of a degree, these are 95% of the uncertainties, to plus or minus 0.04 of a degree by 1980. I only go to 1980 there because I'm showing now the uncertainty that's due just to the time when land surfaces were measured with thermometers, glass thermometers. And after 1980, these MMTS sensors came in, and so I'll talk about that in my next graphic. But in any case, so here we have the published ones going from 0.2 of a degree to 0.04 of a degree in uncertainty. So now we've already seen that even the detection limit of a thermometer, plus or minus 0.2 of a degree, right? Actually, plus or minus 0.4 of a degree, sorry, at the 95% level. So the uncertainty, the maximum uncertainty in 1850 is already half of the detection limit of the thermometers that are being used to measure the air temperature. So on the right side, we see the same air temperature anomaly series, but with the plus or minus 0.4 of a degree of 95% confidence interval just from laboratory uncertainty of the thermometer mixed in with the uncertainties that arise because of the environmental influences on the thermometers when they're used to measure air temperature on the land or sea surface temperature and from buckets and air engine intakes. Well, actually, that's actually a mistake. I'm sorry. This is only the thermometer detection limit error. That's all, 0.432. So when people were measuring sea surface temperatures, they were also using mercury thermometers, and that's included in all this. So you can see that just from the laboratory uncertainty of thermometers alone, that the detection limit of the instruments is much larger than the entire error that's calculated up to the globe in the published record. So the bottom says the whole thing, the published uncertainty at 95% confidence interval is between 2 and 10 times smaller than the laboratory ideal. So those error bars are essentially physically unrealistic. And so if you look at the air temperature record with just the, from 1850 to 1980, the thermometer period, and you want to know what the real change in temperature has been since then, and the anomaly curve is lost inside the detection limits of the thermometer, got no idea what the air temperature change has been. It could be anywhere inside there.
How do you think they can get away with this, with publishing such small uncertainties?
PAL review. You know, it's the same problem with the climate models, right? There are no physical uncertainties in the climate model projections either, and they get away with that too. And you realize when you start studying this stuff, I realized a while back that I saw that there's just no physically valid error bars anywhere. Said if you had them, you can't say anything. Right? If you've got an uncertainty of plus or minus 17 degrees after 100 years, what can you say about future air temperature? Nothing. Right? And if you've got an uncertainty of 0.4 of a degree and plus or minus, and a change of 0.6 of a degree, what can you say about that change? You know, is it real? No, I don't know. You can't say anything about it. How much has temperature changed since 1850? I don't know. It's lost in the laboratory detection limits, right? That's it. And so there's this really weird rejectionist attitude of all these climatologists and global and climate modelers, where they don't want to deal with physically valid uncertainty intervals because it ends up taking away everything they have to say. And, you know, they would have to go back to the gritty reality of doing science, which is really, really hard. And you have to pay attention to all the details. Otherwise, you don't know anything. You know, that's really what's powered me through all of this. You know, I'm an experimental physical scientist, a chemist, an experimental physical methods chemist. I'm not a physicist, but nevertheless, you know, I struggle with all that.
But I'm sorry, we do see press releases and news stories about year X was the hottest year ever. And you ask how much warmer was it? And the answer is like 0.03 degrees centigrade.
Yeah. That's nonsense. It's a completely unrealistic, unresolvable change. But they have the numbers. So they just go with the numbers. You know, the problem is just universal in the field. You know, even the satellite radiometers are not good to better than plus or minus 0.3 of a degree. That's the resolution. People have done calibration experiments, taking radiometers on boats, going out, you know, and they're within 10 or 15 feet of the surface, and they point the radiometer down there and they see how good it does. And that's like 0.3 of a degree, which is what they want. That's, you know, it's pretty good. Really, 0.3 of a degree is it's an accurate measurement when you're talking about 30 degrees. You know, it's 1%. And so you look at the published satellite air temperatures, there are no error bars. There's no confidence intervals on them. They're published as though they're absolutely accurate. And, you know, if you look at an air temperature, the true air temperature, say in 1980, plus or minus 0.04 of a degree, that air temperature is global air temperature is about 18 degrees or so, 15 degrees. So it's 15 plus or minus 0.04. That's what they claim to know. And, you know, it's impossible. You know, if you're in the laboratory and you're going to measure a water bath that's 15 degrees, it's going to be 15 plus or minus 0.4 of a degree. And they're claiming it's 10 times better, and it's outside. So anyway, yeah, I could rant on about the false precision that CO2 climatology lives on. The whole thing is false precision. And I'm just going to say this, and then I'll stop. When you bring that up to the people who work in the field, they get really hostile and rejectionist. They just don't want to hear about it. They've never studied it. They don't know how to deal with it. And they think that you're wrong because they've never heard of it before. It's a foreign concept to all of them. Propagation of air, foreign concept. And, and the people that I work with killed themselves to get things right. Paying attention to all the details, the resolution of their instruments, the errors in their data, how well can they say something? Can they really support their results? And then you go to climate science and people are just all over the place, waving their hands and all the error goes away. So anyway, I'm sorry about that, but you can cut that out too.
Well, do you have any ideas as to why climate science is that way? What's going on? Is it self-selecting who goes into it or what's happening?
I don't know. I think that they are just untrained. I think the climate science, well, whatever climate science is, I don't think there is such a major really. But all the people that I've met who portray themselves as climate scientists know nothing about error analysis, physical error analysis. None of them. The only one I've ever run across who does, Carl Wunsch does, but he's a ocean physicist. And the other reviewer of my climate modeling paper, David Zinchetin, he's an Italian climate scientist, but he understood error analysis. He was very clear in his review of my manuscript that he understood exactly what was going on. And his review was very good, very analytical, very detailed. So he knew, but he's the only one who works as a climate scientist that I know of who actually understands physical error and how to propagate it. The only one. I've written a unpublished manuscript that's available on ResearchGate called Our Climate Modelers Scientists. And when you read that, you see the kinds of things that they say, and your hair will stand up. Really. So anyway.
Okay.
I actually have my last slide has got a bunch of references that might be on there. Okay, so here we go. So now we include the errors that come about because of field measurements, where you have the sun and the wind and the rain and all of the rest of the stuff that are pounding on your measurement device. And you have all of the errors that arise when you measure sea surface temperature with buckets and engine intakes and so on. There calibrations have been done with those things, and I've taken the best calibrations that I could find, and I've included them in the error calculation. Everything is scaled to 30% land and 70% ocean. And I went through and there are records of how much of the sea surface was measured with engine intakes and what fraction was measured with buckets and what fraction was measured with other things. And I've included all of that and ended up with the uncertainty envelope on the right. And you compare that with the published uncertainty envelope on the left, and you can see that obviously when you add the errors that come from the environmental impacts on the sensor, that the uncertainty approximately triples from what it was from the laboratory ideal. And so the published uncertainty, the 95% confidence intervals, those are the same numbers you saw before on the left, are anywhere from 8 to 53 times smaller than the total measurement uncertainty. And so now you look at the anomaly record on the right there, and it's about, 0.8 of a degree and from 1850 to 2010. But it's so lost inside the uncertainty interval that you can't have any idea about how warm it's actually gotten. We know that the climate has warmed up from other observables. One of them is that the growing season has advanced since 1850 by about 2 weeks. And another one that's pretty interesting is that the poleward migration of the northern tree line has been advancing. And going there, above the tree line, trees don't grow because it's just plain too cold. And right at the tree line, trees generally reproduce vegetatively instead of by seeds because seeds won't germinate, it's too cold. So you have trees that grow a root out and then they put a sprout up from the root and they slowly grow that way. That's called vegetative reproduction. So they can do that, but it's really, really slow. And then further south, of course, you get boreal forests. So the line has been slowly advancing because it's warmed up from the Little Ice Age. But the position of the northern tree line today is still about 100 kilometers south of where it was during the medieval warm period, 500 years ago. So it isn't, it's not reached that warm yet as it was 500 years or so ago.
So if the uncertainties are this large using maybe physical thermometers, how big do you think they are trying to use tree rings to figure out a global average temperature?
Those are physically meaningless. You can't get a temperature from a tree ring. You need a physical theory to convert a tree ring metric, density or width. You need some physical theory that converts that into a degree Celsius. But that theory doesn't exist. And so I've written a paper about that. And people just make correlations between certain trees and air temperature. And if the tree rings happen to mimic the air temperature rise, the tree rings are getting broader about the same time the temperature is going up, they say, this tree is a good thermometer, right? And not only is it a good thermometer now, but clearly since it's a good thermometer now, it was a good thermometer during its entire growth period, back hundreds of years. And that's the logic that's used. So they go up to, some place where trees are likely to be thermally stressed, like, high up on a mountain or north in Siberia or the northern Canadian shield. And they find trees growing there and they say, okay, all these trees are temperature stressed. So they take cores out of them, and then they'll do something like do principal components analysis. You get these principal components out and they'll say the first principal component, it's an empirical orthogonal function, right? It extracts out from a data set all of the points that are orthogonal to one another. Okay, and then you have some data points that are left, and then it does a second order extraction of orthogonal data points, and so on. So when they do that with the tree rings, they say, okay, we're up far in the north, or way high in the mountains. So obviously the first principal component is the thermal dependence, and they just assign that, and then they add those all up, stick them onto the end of the temperature record, and say this is what the temperature was back when. That's how it's done. Yeah.
Do you have a sense that in the climate science world, how widespread is the belief that tree rings can be used as thermometers? Do you think it's just
universal?
It is.
Yeah. And there's no physical basis for that because there's no physics in the production of the temperatures from the tree rings. There's no physics in it at all. It's all just statistics. That and fiat. This tree is temperature sensitive. That's it.
I mean, in a bigger sense, do you think that science in general is self-correcting and this craziness in climate science, it's not going to go on for decades more? Any thoughts on that?
It would be self-correcting if there were not very large economic and political interests in it. Yeah. It is self-correcting. Science left to itself is self-correcting because people just can either defend their work or they can't. But criticism has to be free and it has to be vigorous. And it has been in the past. It has been in chemistry, that's for sure. People have gotten very angry sometimes, but it all works out. But in climate science, that doesn't happen. They're doing nonsense. People have shown that they're doing nonsense, and the money keeps coming anyway, and reporters keep, believing them, and the politics are the right because everybody wants to think that we're ruining the earth. And so, off it goes. It just keeps getting reinforced. But it's nonsense. The one thing that's maybe gives you a pretty good idea are the DO18, the oxygen 18 isotope measurements of ice cores. Those, you can measure recent ice cores of recent where the temperature is relatively well known and show that there is a linear correlation oftentimes between the DO18 and the temperature, DO18 and an ice core and temperature. And so you can get a pretty good idea from oxygen 18 isotope concentrations, what the air temperature was back then. And people have correlated that with the borehole temperature, the idea is that these ice cores, when you drill them down, 1,000 feet or so into the Greenland or Antarctic ice cap, that at each annual layer, the ice retains some element of the temperature that was present in the air when the ice froze or when the snow was deposited. And so people will send a probe down the bore and measure the temperature of the ice at stations, very small steps, maybe every centimeter of an ice core. And they'll measure the temperature, and they'll get a variable temperature down the core. And they say that has correlation to what the air temperature was back when that ice was at the surface. And yeah, well, there you go. It's not a very good temperature, but you can still correlate that with the DO18 levels of the same portion of the ice whose temperature you measured. And you can get a linear correlation there back about 4,000 years. So you can have some idea of what temperatures were like from ice core records going back a few thousand years. But that's, in Antarctica and Greenland. That's not anywhere else.
I don't know if I heard you right. That they're not actually measuring the temperature of this ice that's 5,000 years old. Are they using some other proxy, or they're physically measuring a temperature?
They're physically measuring. Yeah, they're sending temperature probes down the borehole and measuring the temperature of the ice. It's bored. Yeah, you can go around to Google Scholar and do borehole temperatures. Search that, you'll find them. I can send you a paper or two if you like.
Oh, yeah, it's just surprising to me that the heat doesn't move around or all this.
That bothers me too. Heat does flow. And there are all kinds of weird things about ice cores that aren't talked about very much. For example, there's chemistry that goes on in them that isn't discussed much, including chemistry that either produces or removes carbon dioxide. The ice core bubbles are treated like bubbles in metamorphic rocks, or granitic rocks. That the CO2 in the atmosphere gets trapped in there and it doesn't change. And people have actually looked at that, and it's a pretty good proxy. The bubbles in ice are fairly close to what the atmosphere was like when the bubble closed. But there are weird things that go on. When the ice freezes in an ice core, in a glacier, or in Antarctica or wherever, it zone refines itself. The ice crystals exclude the salts that might have been in the water that was in that was deposited when the snow formed, or when salt spray got down there, or aerosol chemicals got onto the snow when it was layered down. So those chemicals get excluded from the crystals of ice that form in the glacier, in the ice pack, and they end up in microscopic capillaries of high ionic strength that propagate themselves all through the ice. They're little channels where very salty, cold water is present. That's the zone refined water that has a much lower melting point than water itself does, because it's loaded with salts. So because of that, you've got strange chemistry that can happen in there. Hydrogen peroxide forms because UV penetrates into the ice, and then it goes down these channels and oxidizes some formaldehyde that happened to be down there, and you get carbon dioxide. And so weird things happen, and when you get an ice core that's, 10,000 years old, it's had a lot of time to do weird things down there. So it's tricky business. And sometimes they even find bacteria that are growing, 500 feet down inside the ice pack. Bacteria are growing down there because there's really slow fluxes of carbon that are going through there that the bacteria can use as a carbon source. So, you pull up an ice core, and 500 feet down, there's a purple strip or a pink one. That's where the bacteria are growing.
I had never heard that. Very interesting.
It is interesting. Yeah, there's all kinds of weird stuff going on. That's much more fun than global air temperature. Much more fun. This is probably off subject, but there was a guy named David McKay who worked for NASA Ames in Mountain View. And he was investigating Arctic lakes as models for what you might find on Mars, because it's really cold and really dry, and the air is dehumidified in the Antarctic. So you have these frozen lakes there, and they would drill through. He would drill through, and he actually put on wetsuits and would go down into these lakes in the Antarctic to see what's down there because, they're anoxic and they're really cold like Mars lakes would be. And so, there are things that are growing down there. Weird things go on in these lakes. The Vostok ice core, that when they drilled down there, there's a lake way, way down, buried under the ice down there that's been completely excluded from the atmosphere for 10,000 years or more. And so what's going on there? It's a real tricky business to drill into them because you have drilling muds and so on. You don't want to contaminate the lake. And so there's all kinds of interesting stuff going on that's way, 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 way more fun than just climate science.
I had no idea.
Yeah, it is. Yeah, when I listened to a lecture by David McKay, he had this picture of himself sitting on the lip of a hole that was drilled into the lake in the Antarctic. And he says, this is what happens to government bureaucrats, he said. So you can cut that out too if you like.
I'll leave it in. All right. Very good.
All right. So here is now the conclusion of it all, what we know about future unmeasured average global surface air temperature. And so about global surface air temperature, future global surface air temperature, we know nothing, right? Climate models can't simulate the present air temperature. They can't predict future air temperature. They can't resolve the effect of greenhouse gas emissions. And they can't detect or attribute or project the impact, if any, of human fossil fuel emissions. Okay, so future air temperature is a complete cipher. So about the measured global air temperature, we know a little bit. We know that the climate has probably warmed since 1900, but the rate of warming is unknown. The magnitude of warming is unknown, and there's no evidence that any of the change is unprecedented. And something I haven't discussed is that prior to 1900, the entire surface air temperature record is unreliable. And the reason is because previously thermometers were made of soft glass or lead glass. And when you make a thermometer out of soft glass or lead glass, there are strains left in the thermometer bulb. And those strains work themselves out over time. And as they do that, the bulb contracts. And when the bulb contracts, it forces the mercury or the alcohol up the capillary so that the temperatures you read are warmer than temperatures actually are. So every single thermometer that was made before 1885 suffers from that defect. People, meteorologists who worked back then knew about it and knew that you had to recalibrate your thermometer all the time because the 0 point was changing, because the mercury was being pushed up the bulb, pushed up the capillary. So they knew that. But 20th century meteorologists seem to have forgotten, and it's not taken into account. And so people are recovering temperatures from prior to like 1700 or 1800, and they're putting them into the temperature record as though they're real, but they're not. They're all distorted by Joule drift. It was this drift in thermometer bulbs, this contraction, was discovered in about 1830 or so, 1808, and investigated first at around 1830. And 1844, James Joule, the famous self-educated physicist, decided to do an experiment, and he got a really good thermometer that was just manufactured, and he measured its 0 point for the next 40 years, 13 times. And it was continued. The last measurement of that particular thermometer was in about 1930 or so. It was in a British museum, and it got wrecked during an air raid in World War II. But we have the record of Joule's thermometer experiment from 1844 right up through about 1930. And the squeeze on the bulb caused the temperatures he measured to increase by 0.67 of a degree Celsius over that period of time. So if somebody was using that thermometer to measure air temperature, they would have recorded a 0.67 degree temperature rise that never happened. So
Very interesting.
Yeah, it is. And so this paper that I published on leg metrology and so on includes a long discussion about glass manufacture and the problem of Joule drift, which was investigated heavily in the earlier part of the middle of the 20th century, because people like Coors were making thermometers, wanted to know about it. So they investigated it, and so it's understood very well. But the people who record our air temperature record have completely excluded it from consideration. Anyway, so CO2 climatology lives on false precision, as we've discussed. CO2 climatologists are not trained to evaluate the reliability of their own models or data. They don't seem to know anything about physical air analysis or how to judge the reliability of the data that they've got. So the UN IPCC claim of human-caused climate change has no basis in science. And so effectively, colloquially, they don't know what they're talking about. So the last slide here has got all of the references of the work that I've used to construct this talk. And the one at the bottom you see on CO2 climatology are climate modelers, scientists. You might want to take a look at that one. You will especially like that discussion of the kinds of things that climate modelers believe. For example, that plus or minus 70 degrees temperature uncertainty is an actual physical temperature. That means that the model is oscillating back and forth in between temperature extremes. That's, it's the most incredible thing. Anyway, so there they all are. Anybody who wants to check my work can do so.
Okay, very good. And I put this PDF up on my Substack. I'll put a link to that so that you can go in here and people can just click on those links and read up on all of Patrick's work. You don't actually have to type in all those URLs. So that's good.
That's a good thing. Yeah.
Okay. I'd like your opinion on, do you have ideas on what the effect of volcanoes are, for example, or geologic heat on the climate of the Earth, or the Earth's magnetic field? Either one of those two things. Any opinion at all on a big or small effect?
Well, one thing that's interesting is this. A year ago, there was a very large volcanic explosion in the South Pacific. You know about this, the Hunga explosion. That increased that shot a plume of water up into the stratosphere. It was very unusual, and it increased the humidity of the stratosphere by about 10 to 15%, which is a lot. Trillions of gallons of water got shot into the stratosphere, and those are going to cause the climate to warm up because stratospheric water has an impact on the climate, on the troposphere. So that will be pretty interesting to see how that all works out. One thing that I do want to say in the context of what we've talked about so far is that this paper that I found in 2003, a paper by Willie Soon and Sally Baliunas and Craig Idso and Kondratyev and David somebody, that paper is on the uncertainties of climate modeling. And it talked about the gigantic errors that climate models make when they simulate the climate. Really large scale errors, especially in the ocean. But the errors are so gigantic, tens to hundreds of watts per square meter compared to a perturbation of 35 milliwatts, that it becomes immediately obvious that the IPCC couldn't know what they're talking about, and neither can anybody else. And in any well-functioning science, that paper would have put an end to it all, the whole global warming thing, because nobody can tell from modeling what the temperature is going to do with these emissions. It's that you saw the errors that I pointed out, but those are only 4 or 5, plus or minus 4 or 5 watts per square meter. When you have errors that is like plus or minus 50 watts in the energy state of the climate, you can't tell what's going on. So that just shows how awful climate science has become. That a paper like that can be published. There were 4 challenges to it that are in the literature that were published by climate modelers who were very angry that somebody revealed their, quote, dirty laundry, unquote. And they ignored and just dismissed that result and just went on as before, as though nobody had ever disproved the entire focus of their work. So, in a well-functioning science, that would have put an end to everything. I mean, wouldn't have had any of this agony and trillions wasted and birds chopped and bats exploded and children frightened and huge amounts of money going into the pockets of already wealthy people and families forced to live with indoor smoke and excess winter fuel poverty deaths because people have to choose between putting food on the table or heating their house. None of that would have happened. None of it. So there is an implicit criminal negligence in modern climate science because they don't hew to the ethics of real physical science. Right? The ethics of real physical science is you're honest about what you're doing, you're really rigorous about details, and you really pound down so that you know when you know something. And they don't do that, and they're hostile to it. And as a consequence, we have all of these abuses that have happened. So that is very upsetting to me as well.
Do you have any advice on what can be done to bring sanity back or to fix it as quickly as possible?
Well, Well, I mean, what has to happen is that pretty much all of climate science has to be defunded. Richard Lindzen has said pretty much the same thing, and I completely agree with him. The only way that consequences happen is if the money stops flowing. And so that's what has to happen. So people who are out there who are listening to this should contact your Congress people and tell them that it's all nonsense. And you can use my work or other people's work or Willie Soon's work or Sally Baliunis's and all the rest of these really good scientists who have published on this to make your point that climate modelers and the climate scientists in operation today don't know what they're talking about. And all this money that's being spent and all of the solar and wind power and batteries that are blowing up in people's cars, it's all for nothing. It's all for nothing. It's all wasted. It's lucky we're as rich a society as we are because we've wasted trillions of dollars and people are still living mostly okay, but it's all going to go away. So people need to I've contacted my congressmen. You need to contact your congress people and insist that they vote against all this stuff and vote them out of office if they won't do it. That's the only peaceful way we have of solving the problem.
Okay. On that note, I think we will wrap up. Very good stuff. Thanks for taking the time. I hope to have you on again. I learned a lot from what you said here today. So
thank you, Tom. I really appreciate it. And I really appreciate the opportunity and honor of being on your podcast.
All right. So we'll talk to you next time. Patrick, Frank, thank you. Bye.
Thank you.